Imagine you need to track a flock of 456 sheep, and your only method is drawing one line per animal. This is one-to-one mapping. For the first few sheep, it works perfectly, but as the flock grows, the visual evidence becomes an unreadable blur. Early humans organized this chaos by grouping marks. A diagonal slash across 4 lines creates a bundle of 5, which helps you read a small number like 8 at a glance. But zoom out to that flock of 456, you still have nearly 100 separate bundles to count. The friction remains. One-to-one mapping makes intuitive sense to our hands, but it places a hard limit on our ability to track complex data. To scale up and build economies, civilization required a method that compressed massive quantities into a handful of legible symbols. This papyrus reveals how the ancient Egyptians approached the problem by establishing a base 10 system. Instead of single tally marks, they created distinct visual symbols grouped by powers of 10, landmarks for 10, 100, and 1000. To record a number like 324, they used an additive method. You draw 3 hundreds, 2 tens, and 4 ones. Grouping by powers of a fixed number made recording larger quantities much easier than carving hundreds of individual tallies. But because this system relies purely on adding symbols together, writing the number 9 still requires you to draw 9 individual marks. When applied to large-scale arithmetic, the sheer volume of repeating symbols makes calculations slow and cluttered. Look at this weathered Latin inscription. The Romans attempted to fix the symbol clutter problem by introducing midpoint markers. By assigning symbols like V for 5 and L for 50, they reduced the number of strokes needed to carve an inscription. They also introduced a spatial rule. If you write X followed by V, you add them to get 15. But if a smaller symbol is placed before a larger one, you subtract it. A V with an I placed after it is 6. An I placed before a V is 4. This introduces rigid complexity. Try converting 49. You cannot simply write I followed by L to subtract 1 from 50. You have to construct the 40 by subtracting 10 from 50 to get XL, then construct the 9 by subtracting 1 from 10 to get IX. The result is XLIX. While this logic reduced the physical space numbers took up on a monument, it created a severe operational bottleneck. Mixing additive and subtractive rules meant doing math with these symbols was inefficient, forcing merchants to rely heavily on physical tools like the abacus. The solution emerged from the Hindu-Arabic system. It replaced the idea of adding separate symbols with the concept of place value, where the physical position of a digit dictates its magnitude. Take a number like 456. With just 10 basic numerals, we can express infinite scale by assigning them to specific columns. The 4 drops into the hundreds column, the 5 into the tens, and the 6 into the ones. But a strict place value system faces a critical failure point. What happens when a column is entirely empty? Look at 707. If you don't have a way to represent the empty tens column, the 7 in the hundreds place slides over, and the number collapses into 77. This dot served as a structural placeholder, a tangible spatial anchor designed to lock other digits into their correct base powers. Combining positional columns with the 0 placeholder allowed for universal, scalable calculations that could be performed entirely on paper. When we put these systems side by side, the mechanical difference is clear. The Egyptian system is additive, requiring a massive accumulation of symbols. The Hindu system relies on place value, uses 10 digits, and utilizes a 0 placeholder. We started with the visual chaos of one-to-one tally marks, reduced friction with Roman numerals, and finally arrived at the elegant positional place value system. The modern number system is a highly engineered technology, refined over thousands of years of trial and error to make the infinite readable.